There's a lot of confusion about gravity out there, so this will just be one part of a series on gravity. Today, I want to cover the centrifugal force caused by the spin of the Earth. How does the Earth's spin interact with gravity? Putting that another way, how can water stick to a spinning ball? The question goes a little something like this. The Earth is spinning at tremendous speed. It's actually faster than that, but let's just roll with it. That's a lot of centrifugal force, and blah, 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 blah. It's faster, it's so fast, it's 1,000 feet per second, more like 1,000 miles an hour. The Earth spinning at that speed would be tremendous force, and we must be superheroes. Woo! Before I go on, I feel like I need to address this. Somebody out there is going to insist that centrifugal force isn't real. They'll either want to nitpick or they'll want to cherry pick. I really don't want to pick nits or cherries. We all understand that you feel a force. First question, what is the equation for centrifugal force? F equals mv squared over r. What do we know here? M is the mass of whatever object we're talking about. This is not the mass of the Earth. In our discussion, this is the mass of whatever object we want to weigh here on the Earth. V is the linear speed at the rim of a rotating circle. R is the radius of that rotating circle. First, let's use a 1 kilogram mass and place it at the equator. At the equator, the radius is 6,378 kilometers, or 6 million meters. What is V? That'll be a short calculation. The circumference of a circle is 2 pi r. For the Earth, that comes to 40 million meters. The Earth rotates once every 24 hours. Actually, it's 23 hours and 56 minutes if you want to get technical. So at mean sea level, on the equator, the surface moves at 465.1 meters per second. That's over 1,000 miles per hour for those of us more comfortable with those units. You hear that number from time to time. 1,000 miles per hour sounds pretty fast. Seriously, the Earth spinning at 1,000 miles per hour? That's got to create a tremendous centrifugal force. Let's find out. F equals mv squared over r. M is 1, V is 465, R is 6,378,000. The centrifugal force is, are you ready for this? 0.03 newtons. That's 0.008 pounds to you and me. Next, I think we should put our 1 kilogram test mass on a scale and weigh it. We'll call gravity 9.807 newtons per kilogram. At the equator, the centrifugal force acts in the opposite direction of gravity, so we'll subtract that. Our mass should come in at 9.773 newtons. That comes to about 1/3 of 1%. So our test mass at the equator weighs about 0.3% less than it would at the poles. So let's try putting our test mass up at a higher latitude. I've got it here at 45 degrees. Gravity still points towards the center of the Earth, and we'll still make it 9.807 newtons. The Earth spins around this central axis, so the radius of the spin at that higher latitude is smaller. That's going to come in as the radius at the equator times the cosine of 45 degrees, approximately. Okay, that comes to 4.5 million meters. And that gives us a circumference. The circumference of this spinning, rotating circle right there comes out to about 28 million meters. Now, the Earth still spins, no matter what latitude you're at, it still spins in about 24 hours. our velocity at the surface of the Earth at this point comes to 328.9 meters per second. I've calculated what the centrifugal force is for that, and I got 0.02399 newtons per kilogram. Now, that force will point outward from the rotation angle, which is in that direction. We need to add these two forces together. Both of these forces act on our test mass, and they act in different directions. And when you do that, you simply need to add the two vectors. The easiest way to think of adding vectors is simply to put them head to tail, like this. So we've got gravity pointing at this perfect 45-degree angle down, and we've got the tiny centrifugal force pointing horizontally outward. Together, these two angles add to give us the resultant, drawn in purple, effective net weight. Let's zoom in on that a little bit and get a better idea of exactly what's going on. We have the gravity pointing at 45 degrees, and we have the centrifugal force pointing directly to the right. Together, these two forces add together to give us the combined force. If we were to put this weight on a scale, the combined forces would push down on the scale. That would be the weight we're going to measure. So, how much is this purple line? This vector points at 45 degrees, so let's break that into a horizontal and vertical component. Some amount of this vector points to the left, and some amount of this vector points down. We can split this vector up into its two components using a little bit of trigonometry. Remember that these inside angles were 45 degrees. When we have a right triangle, like we have here, the opposite over the hypotenuse is the sine of the angle, and the adjacent over the hypotenuse is the cosine of the angle. So that allows us to calculate the opposite and the adjacent like this. If the hypotenuse is 9.807, then multiplying by the sine of the angle, we get 6.935. So along the top here, we have 6.935 newtons. That's how much of this vector points to the left. The rest of this vector points down. As you can see, part of this vector points to the left, part of this vector points down. How much is down? Well, it's a 45-degree angle, and at 45 degrees, the two sides are equal, so that's also 6.935 newtons. The centrifugal force, the red arrow, points directly to the right, so breaking that into a horizontal and vertical component is a little bit trivial. Let's use these components to calculate the final results of the purple vector. Just like with the green vector, we can split the purple vector into the horizontal and the vertical parts. The vertical part of the purple vector points downward, and since the red arrow contributes nothing in the vertical, we can just copy over the 6.935 to the purple vertical component. How about the horizontal? In the horizontal components, the green points to the left with a value of 6.9, and the red points to the right at 0.024. We add those together, and we get 6.912. That's 6.935 minus 0.02399. The question then is, how much is the combined force? We have the combined force pushing down the y-axis, and that is 6.935, and the combined force pushing to the left along the x-axis, 6.912. We can use the Pythagorean theorem with this right triangle to calculate the length of the hypotenuse. The Pythagorean theorem was c squared equals a squared plus b squared, or c is the square root of a squared plus b squared. We plug those numbers in, and we get 9.79. 9.790 newtons. Our original gravity vector was 9.807, but now at 45 degrees latitude, we measure a combined force of a little bit less, 9.79. How much less is that? Well, it's this much less, as a fraction of the original, is that much less. If we express that as a percent, we get 0.17%. So less than 0.2%. At the equator, you'll recall, we got about 0.34%. And here at 45 degrees latitude, we get 0.17%. That means our object is a little bit heavier at 45 degrees latitude than it was at the equator, but not as heavy as it was at the poles. So what does Larry have to say about that? Well, it looks like Larry thinks you only weigh less directly on the equator. He seems to be confused about the fact that the centrifugal force doesn't line up perfectly with gravity, except if you're on the equator. He's pretty sure that that means that you only weigh less on the equator. So let's take another look at this. This is how much you would have weighed if there was no centrifugal force. So that would happen at the poles. Because there's a centrifugal force, we have to add the two together to get our net weight. And we just showed that the net weight is going to be slightly lower everywhere except the poles. Earlier, we did one for when you were at the equator, and the two vectors lined up perfect. And at that point, we got about 0.3% drop in weight. Here at 45 degrees, we got less of a drop in weight, but we still get a drop in weight. In fact, you get a smooth curve where you weigh the least at the equator, the most at the poles, and of course it's a smooth blend everywhere in between. As you can see from these comments, Larry has become quite concerned about the angle between gravity and the centrifugal force. We've shown the impact of the centrifugal force on the weight of an object, but Larry also noticed that there is now an angle between the two forces. Down at the equator, gravity and centrifugal force lined up perfectly, but up at 45 degrees north, the centrifugal force seems to be pointing a little bit to the south. Won't that make objects start rolling down towards the equator? I don't mean to be picking on Larry here. Larry is right that there's an angle here, and he's not alone there. I was planning to include a video clip from Antonius Subrats where he was pointing out this issue back in January. Unfortunately, that video is gone now, but the point is, people have noticed this angle, and we need to take a closer look at it. I'll give him credit for this much. The angle exists. We saw that when we calculated the effective weight at 45 degrees latitude. There is a tiny angle in the direction of the net force and the direction the gravity points. I've exaggerated here in this diagram, but make no mistake, it's there. But will that cause things to roll south? Let's take a closer look. I've got gravity in green and centrifugal force in red. We're up at 45 degrees latitude, so this diagram matches what we've been doing so far. Let's rotate the diagram to a sensible orientation where gravity points down. There you go. We have the ball sitting on a perfectly flat surface. Gravity pulls the ball straight down, so there's our centrifugal force, right up there. The centrifugal force is pointing upwards a little, and that makes the ball a little bit lighter. But notice how it also points to the right. Isn't that going to make the ball start rolling? I can cut you some slack if you think so, because this diagram sure makes it look like it should, but it won't, and the reason for that is more subtle than you might think. You may be thinking the red arrow is just too small to do anything, but no, that's not it either. Perhaps the best way to see why the ball won't roll would be to imagine doing this experiment. The first thing we need to do is establish that the surface is perfectly flat and level. Did you catch that? That's the trick right there. we need our surface to be level. How do we do that? Let's rig up a plumb bob like so. When the bob is perfectly centered, we know we have our surface level, right? We can do the same thing with a spirit level. Do you see it yet? What makes that plumb bob hang? Normally, we simply answer gravity. But we just showed that that isn't entirely accurate, is it? The centrifugal force from the Earth's rotation is small, but it's there. That means our plumb bob hangs like this. So now we place the ball on our level surface. You tell me, which way will the ball roll? The diagram is still a little confusing at this point. It's hard to say what the ball is supposed to do. Remember, the purple arrow is the result of the combined forces. It's the purple arrow we feel. It's the purple arrow we used to level the surface. The purple arrow, not the green arrow, defines level at this location. So let's straighten out the diagram to show what level means. Now it's pretty clear that the ball isn't going to roll anywhere. I can hear the complaints in my head already. Somebody is going to insist that we wouldn't level the surface by the purple line. We were going to align it to gravity. Right, sure we were. How did we measure gravity exactly? A spirit level? A plumb bob? How do you propose to eliminate the centrifugal force the spirit level feels? You can't. The force we feel, the force we normally refer to simply as gravity, is the force that defines what level means. As we've just shown here, that leveling force isn't technically gravity working alone. The force we use to level our paintings on the walls, the force we use to level the floors of our homes, the force that causes water to find its own level, includes just a tiny bit of centrifugal force. And no, it doesn't point perfectly toward the center of the Earth. Aha! If gravity doesn't pull everything directly to the center of the Earth wouldn't be a sphere. Gotcha! Well, if you think that, congratulations. You're right. But you don't gotcha anything. Remember that oblate spheroid nonsense the flat earthers love to make fun of? Oh yeah, that. If level is actually angled slightly, the Earth would not be a perfect sphere. It would have to be very slightly wider at the equator than it is at the poles. We need level to be a curve that's almost a sphere, but just a little bit squashed. It's just a little bit oblate. Okay, but if that were really true, then why has nobody ever mentioned this before? Every Globie I've ever heard said water was flat because of gravity. Nobody ever mentioned centrifugal force. Gotcha there. It's true, we don't normally mention the centrifugal force in this context. But there's no gotcha here either. We don't mention it because it's a teensy-weensy little force. It's a fraction of a percent. What's more, even if we were worried about that amount, we only feel the combined force. It would take precise astronomical observations to detect the difference. So who would bother with that? The combined forces act on us, our plumb bobs, our spirit levels, our accelerometers, our airplanes, and even our pendulums. That combined force is how we define down, and it's at least 99.7% gravity. Those of us who have developed a healthy relationship with science education understand that this is how it works. There's always some additional detail, some subtler nuance that goes beyond the scope of what we've covered so far. There's always something more to learn. This isn't a flaw in science education. This isn't a gotcha. This is how we learn. We learn a little bit at a time, and the field of science itself works like this too. Scientists keep discovering new details and refining their models year after year. That's not a gotcha. That's kind of the point. So the rolling ball test isn't going to prove anything, but all is not lost. We can still test this hypothesis. All we need to do is measure a test weight in various places on the Earth. We showed that we cannot easily detect the angle created by the centrifugal force, but we can detect how it reduces the total weight, even if it's only by a tiny fraction. Check out Critical Think. He's done that for us. I'll link all 3 videos he made in the series below. He goes into more detail than I have here. Remember that oblate spheroid thing? That makes an appearance. Or is that an appearance? The short version is if you want an accurate estimate of gravity, you should use the WGS-84 model, which includes centrifugal force as well as altitude and accounts for the oblateness. Altitude? Wait, what? Remember how I said science education always leaves out some details? Yeah, I've glossed over some stuff even here. There's always more to learn. Spoiler alert, turns out the Earth is a spinning globe. Sorry if I ruined the surprise ending on that one.